Hello. Today we shall discuss about context-free grammars, a language-defining construct for describing context-free languages. We know that regular expressions are used for describing, defining regular languages, and finite automaton is a mathematical model which will accept all regular languages. In order to describe the non-regular languages, we need more powerful language-defining structure. Example for languages which are not regular are a language L1 it consists of strings of the form a to the power n, b to the power n plus 1, where n is greater than or equal to 0, or a language L2 which is consists of all string w which is of the form palindrome. These are two examples for non-regular languages for which we cannot describe or design finite automata. Languages that are generated by context-free grammars are called as context-free languages. If a language L is accepted by finite automata, or if a language L is described by regular expression, then L also can be generated or described by context-free grammar. But the converse is not true. All context-free languages cannot be described using regular expression. There are few languages for which we cannot design finite automata or we cannot describe these languages using regular expressions. The definition of the context-free grammar has four tuples that are V, P, P, S, where V is a finite set of variables or non-terminals, P is a finite set of terminals, P is a finite set of productions or rules which are of the form A giving alpha, where A is a variable and alpha is a string of 0 or more length consisting of variable or terminal. S is a start symbol which is a variable, and then in all the productions on the left hand side we have only one variable which makes the grammar as context-free. Example for the context-free language can be a language L which is of the form a to the power n, b to the power n plus 1 where n is greater than or equal to 0. The grammar for this languages can be consisting of four tuples S which is equal to S in this example, and the terminal is consisting of symbols A, P, and the production we have two definitions for the variable S, where one is a recursive definition S giving ESP and another is a non-recursive definition S giving B. The recursive definition will generate all strings of consisting of number of A is equal to number of B's, and the additional B we can get it from the production S giving B. And the starting variable is S. Derivation. Derivation is a process or procedure to prove that a string can be generated from the given grammar. Now, in order to generate the string, we repeatedly apply the production rules, starting with the start symbol, and we have to end it with the given string. The derivation can be one step, or it can be more than one step, or it could be zero also. The definition for the one-step derivation is represented as U gives string B. If U is a string X alpha Z, and we have to derive the string B as X beta Z. If and only if we can, there is a production alpha giving beta and P. Then we say that U can derive the string in one step B. This can be generalized for 0 or more step, which can be represented as U in multiple 0 or more steps that we start generates string B, which is they're using a sign of one derivation, which is of the form U giving U1, which gives U2, finally it gives B. If it is a one-step derivation, U in one step directly gives V1, or if it is 0 step derivation, then U is equal to V. So what is a context-free language? Given a context-free grammar GVPTS, the language generated or derived from G is the set of all string W, where W can be generated starting from the starting variable S using 0 or more steps. So the language consists of all the strings which can be generated from the starting variable of the grammar definition. So this is called the language of G, which can be written as L of G. Consider another example, language where L is equal to W, where W is a palindrome and the alphabet A, B. The production consisting of four definitions for the variable S, where the string definition will see to that any string which starts with A, which also ends with A, and any string which starts with B, which also ends with B. And the last two are non-recursive operations which will generate all the palindromes which are of odd length. The starting variable in this is yes. If I want to generate the even length palindrome, I need to have another definition for the S, where S is epsilon. An example for non-regular language would be a language of the form A to the power n, B to the power n, C to the power n, where n is greater than or equal to 0, for which we cannot describe using context-free grammar. Now, past-free is a free representation of the derivation, wherein each internal node is labeled with the variable b, and each leaf node is either a variable or terminal or epsilon. If the leaf node is epsilon, then it must be the only child of its parent. If the rule A gained A1 to AN occurs in the derivation, then A is a parent node of the nodes labeled A1 to AN. As shown in this diagram. If we say that there is the definition of the grammar has product in SPV AS, or the product in SPV SP, or SPV epsilon. Now, in order to generate the string of the language, you can have many possible derivations. Since in order to resolve this ambiguity, we use only two types of derivation, that is leftmost derivation and rightmost derivation. So what is leftmost derivation? The leftmost derivation in LMD is in this. At each step of the derivation process, we replace the leftmost variable of the by one of its production values. Whereas in rightmost derivation, RMD, at each step of the derivation process, we replace the rightmost variable by one of its production values. Consider an example where the grammar is described using the step of production S given A, A, B, and A is defined as the fourth production, as well as similarly B is defined as the third production. In order to generate the string here, A, B, B, we start with the starting variable S in both the types of derivation. Whereas in leftmost derivation, in the after S, at the second step, we choose the variable A for replacing it with the definition, whereas in the rightmost direction, we choose the variable B for replacing it with its definition in the third step. So in the leftmost derivation, the variable A is replaced by the definition of the variable of its definition. Similarly, in the third step, we choose once again the variable with its definition. In the fourth step, the second A, that is the non-terminal A, is replaced with its definition. So at each step of the derivation, we choose the leftmost variable in the sentential form, which has to be replaced by its definition. Similarly, in the rightmost derivation, we choose the rightmost variable for replacing it by its definition. So these are the derivation for a string that belongs to the language, either using LMD or RMD.